For example 1, I'd like to try to find the inverse function for something a little bit more complicated. F of x equals 2x plus 1 divided by x minus 3. So to do this, if the function is y is equal to 2x plus 1 divided by x minus 3, the inverse is the function that just switches out all the x's with y's and vice versa. So technically, x equals 2y plus 1 divided by y minus 3, this is the inverse. Every x and y has been changed. But I want to write this in a way that's more useful, and that just means you now have to solve for y. So that's what's going to be tough about this problem. It's like, how do I actually solve this equation for y? And there's not a whole lot of options to start with, but what I'm going to first do is multiply both sides by y minus 3. So I get x times y minus 3 is equal to 2y plus 1. Again, like, not too much to do here, so I think the only option at this point is to distribute the x on the left, which gives me xy minus 3x is equal to 2y plus 1. So we've taken the first equation, switched it out to its inverse, and now we've just manipulated the equation as best we can. The trick here is to take everything that has a y, the thing you're solving for, and to put it on one side. And anything that does not have a y, move it to the other side. That will actually be useful in this process. So I'm going to subtract 2y from both sides, but I'm also going to add 3x to both sides. It doesn't look like it really helped us very much. I'm just reordering things. However, on the left, since everything has a y, keeping in mind that's the thing you are solving for, you can now factor it out of both terms on the left. So the left side is the same thing as y times x minus 2. And I'm not doing a thing to the other side of my equation. So why that is useful is it's now very easy to solve for y. You can just divide both sides by what was remaining after you factored out y. And here's my answer. Y is equal to 3x plus 1 divided by x minus 2. And maybe just to write this up at the top, the notation we were using is, if my original function is f to the negative 1, that symbol just indicates that I have found my inverse function. So it's 3x plus 1 over x minus 2. And there's a lot of things to point out with this example. If your inverse is the thing that switches out all of your x's with y's and vice versa, one interesting thing to do is to compare your vertical and horizontal asymptotes. For example, in this original function, x equals 3 is the vertical asymptote because it makes the denominator 0. The horizontal asymptote is going to be y equals 2 over 1, or just y is equal to 2. If your inverse switches all of your x's with all of your y's, that is true for this x and for this y. This should now be a y, this should now be an x in my inverse function. That is, I should have that y is equal to 3 and x is equal to 2 as being relevant to my new equation. And what do you know? It is. The vertical asymptote is now 2, x is equal to 2, and the horizontal asymptote is 3, which is y equals 3, which makes sense if you compare the coefficients in front of your x's. So it's nice to, when you get your answer, think about if the new equation you have is in fact the inverse, or maybe you made a mistake along the way. But for this problem, I'll leave it at this is the answer, and it's kind of up to you to check a couple of things to make sure that your answer seems to be correct. Okay, for example 2, the point of this example is to show that if you're just given a random function, for example y is equal to x squared, something pretty simple, sometimes it's impossible to find a function that is an inverse. So here's what I mean. If I look at the function y equals x squared, I'm just going to randomly choose a couple of points on it. Actually, it won't really be so random, but here's the point 2 comma 4. And over here is the point negative 2 comma 4, an x value and a corresponding y value. On the inverse function, if the original function has the point 2, 4, on my inverse, you'd have to have the point 4, comma 2, because 2 is an x, 4 is a y. My inverse switches those two things around, and the same thing has to be true for negative 2, comma 4. On my inverse, you would have to have 4, comma negative 2. The problem is that if I plot both of these points, 4, comma 2 and 4, comma negative 2, that can't be a function. I mean, here it's failing this vertical line test. So visually, it is really easy to see if your function does not have an inverse. It's called the horizontal line test. If you can find a single horizontal line, it just has to be one, that goes through the graph 2 or more times, it means that your function does not have an inverse. So this is the horizontal line test. So like if I look at this example now and I say find the inverse of y is equal to x squared, I know that that's actually impossible to do because I found exactly one horizontal line that went through the graph in 2 places. And it can be, just one line. It doesn't have to be the one I chose. Like you don't even have to define points. You could just say, oh, like, hey, here's a problem. Like I get these 2 points here and here. That's an issue. Or this would have been acceptable too. Like it goes through here and here. Once you find one line where this happens, you're done. Another thing to maybe expand on this a little bit would be you would have noticed that something would have gone wrong in the process of trying to find your inverse. By that I mean the original equation is y is equal to x squared. The inverse is x is equal to y squared. To solve for y, you'd have to take the square root of both sides. But as we've seen, you get plus or minus the square root of x is equal to y. You actually get 2 different functions, and like which is it? Is it the positive one or the negative one? So that's a problem right there. But the point of this example is if you look at a graph and you can find a horizontal line that goes through the graph in 2 or more places and it happens just once, there is no inverse for that function on its given domain. We actually have some terminology that says this is not one-to-one. If a graph is one-to-one, it has an inverse. If it doesn't, it does not have an inverse. And for the final example, example 3, I'd like to try to find the inverse of the function y equals the square root of x minus 2 plus 1. What's going to happen in this example is we're going to get an inverse function, but something's going to be a little bit incorrect about our answer. So I included the graph here because before we even get started, I want to state the domain and range of this original function. I can look at the graph and see the domain goes from 2 to infinity. No surprise, since I have the square root of x minus 2, it moves 2 places to the right. And the range is from 1 to positive infinity. Again, that plus 1 at the end means your graph moved up 1 place, my graph is increasing, so here I have my domain and range. The thing to point out is that your domain is your x values, the range is the y values. So it should be that on your inverse function, these are going to be backwards. The domain of my inverse function should be 1 to infinity. The range of my inverse function should be 2 to infinity. So let's see what happens. I'm going to take my original function, I'm going to call that y an x, and the x a y, and note that this thing is my inverse. The only difference is I'm going to solve it for y. I'll do that by subtracting 1 from both sides. And the last step being, second to last step being, I'm going to square both sides. And on the left, I'm actually going to leave it as x minus 1 squared. On the right, I get y minus 2. I will add 2 to both sides, and I'm at my answer. I get that the inverse function is x minus 1 squared plus 2. Now, the problem is that this has a domain of all real numbers. But that can't be my answer. That can't be correct. The domain of this function should be the range of my original equation. Again, the reason is the range is your y values. On your inverse, it would have to become your x values. Why this is important is if you graph x minus 1 squared plus 2, I could even try to like sketch it in on my equation over here. It's a parabola. It would look something like this. But that's bad. I mean, you can't have an inverse that isn't 1 to 1. It also has to have an inverse of the original function itself. And the solution here is if we include the domain of 1 to infinity, it essentially means you're just erasing the left side of the graph, the part that's causing an issue for it not being 1 to 1. So basically, the graph starts at 1 and it goes towards infinity, and that matches up with the domain that we have over here. So you just gotta be a little bit careful. If you get an answer and your graph is not 1 to 1, you have to change the domain so it is, but it's not very difficult to do. You can just look to the original function to figure that out.